Okay, so like one of the biggest mysteries in the universe is, right, this thing called dark energy.
Yeah, it's pretty wild, really.
And it's like making the universe expand faster and faster, but we don't even know what it is, you know?
Exactly. We know it's there, we see the effects, but what is it? Huge question mark.
And that's like what we're going to deep dive into today.
We're going to see if it's, always been the same or maybe it's changing like over time.
Right, and we're looking specifically at these hints from, what is it?
DSI, the Dark Energy Spectroscopic Instrument.
Yeah, DSI. Pretty cool name, right? So for everyone listening, we're going to break it all down, like what DSI is all about, what it's found so far, and why everyone's like kind of freaking out about it in the cosmology world.
Yeah, it's causing quite a stir.
All right, so first off, what exactly is this DSI thing?
So DSI, it's an instrument. That's what it is, right there in the name. And it's basically taking these like super detailed light readings from these really, really distant galaxies, like a cosmic census, but instead of people, it's galaxies.
And this census isn't being taken from space, right? It's right here on Earth.
Yeah, I got it. They actually retrofitted DSI onto an existing telescope, the Mayall telescope it's called. It's at Kitt Peak National Observatory in Arizona. They picked that spot because the sky is like super clear and dark up there, perfect for, peering way out into the universe.
Makes sense. So its main gig is figuring out dark energy then.
Yeah, that's the heart of it. It's all about understanding how the universe has been expanding over time. And, because dark energy is driving that expansion, by studying one, we learn about the other. And it does this by taking these, what we call spectrographic surveys of galaxies, billions of light years away.
Spectrographic. So it's not just like taking pictures, it's examining the light in a specific way.
Yeah, exactly. Think of it like this. At the heart of DSI, there's this focal plane, and it's loaded with 5,000 tiny robotic positioners. 5,000, it's kind of mind-blowing. Each one of those little robots can aim a fiber optic cable at a single galaxy. And the light that they capture is then sent to a bunch of spectrographs, which are basically like high-tech prisms. They split the light into all its different colors. And by looking at that spectrum, scientists can figure out all sorts of things about the galaxy, like its redshift, how much its light has been stretched because the universe is expanding. That tells us how far away it is and how fast it's moving away from us.
5,000 little robots. That's crazy. So when did this whole thing get started?
Officially, the main DSI survey kicked off in May 2021, and it's supposed to run for 5 years. So right now, as we speak, it's still collecting data.
All right. And who's the brains and the money behind this whole operation?
Lawrence Berkeley National Laboratory, they're running the show with a lot of support from the U.S. Department of Energy's Office of Science, and a bunch of other institutions are involved, too, from all around the world. So it's a real, global effort to understand these, universe-sized mysteries.
Right. And it's not just dark energy, right? It's also tackling a bunch of other big questions about, the nature of the universe.
Yeah, totally. I mean, dark energy is the big one, obviously. But DSI is also trying to build these incredibly detailed three-dimensional maps of the universe, which would be, amazing to see. And from those maps, we could do all sorts of things like really test Einstein's theory of general relativity, or figure out the masses of neutrinos, these super tiny particles. We might even be able to get clues about the super, super early universe.
So lots on the agenda. Okay, so how does DSI actually go about measuring the expansion of the universe? I remember you mentioned this thing, what was it? Baryon acoustic oscillations?
Oh, yeah. Baryon acoustic oscillations. BAO for short, because, scientists love their acronyms. So imagine, right after the Big Bang, you've got this incredibly hot, dense plasma, and sound waves are rippling through it. Those sound waves create this kind of a pattern in how matter is distributed, and that pattern, it shows up in how galaxies are clustered together, even billions of years later. It acts like a standard ruler, a yardstick that's, imprinted on the universe.
So we know how big this ruler should be, at different points in the universe's history.
Exactly. And that's how DAI measures the expansion. It looks at how big that BAO pattern appears at different distances, which correspond to different points in time, right?
Yeah.
Because looking farther away is looking back in time. And by seeing how much that pattern has stretched, we can figure out how much the universe has expanded over time. It's pretty ingenious when you think about it.
It is. So how many, galaxies and things is DAI going to look at over the whole project?
It's going to be a lot, a lot. By 2026, they're expecting to have observed something like 40 million galaxies and quasars.
Wow, 40 million. That's 10 times more than the Sloan Digital Sky Survey, right?
Yep, and Sloan took 20 years to do its thing. DSI is collecting data way faster.
That's amazing. And all this data, it's not just like hidden away in a vault somewhere, right? Other scientists and even regular folks can get access to it.
Absolutely. DSI is all about open science. They've already released some of the data publicly. They had an early data release back in June 2023. And then the big one, Data Release 1, came out March 19th, 2025. It had like 18.7 million objects in it. Researchers anywhere in the world can get their hands on it, which is, pretty awesome for science as a whole.
Okay, so we know what DSI is, how it works. What's it telling us about dark energy? Like, what are the big findings from the first 3 years?
So they looked at about 15 million galaxies and quasars from those first 3 years. And the biggest finding, the thing that's got everyone talking, is that when you combine DI's data with all this other evidence we have about the universe stuff, like measurements of the cosmic microwave background radiation, observations of distant supernovae, and studies of something called weak gravitational lensing, all together, it looks like maybe dark energy's influence has been, like, decreasing over time.
Wait, decreasing? That's huge.
Yeah, it's a pretty big deal.
Huh.
Because, for the longest time, we've been working with this model of the universe called the Lambda-CDM model. And in that model, dark energy is like this constant thing, the cosmological constant. It never changes. And actually, if you look at just DSI's data by itself, it still kind of fits with that model.
So it's when you put it all together, DSI's data with all the other stuff, that's when it starts to look like maybe dark energy isn't so constant after all.
Exactly. It's that combination, that convergence of different types of evidence that's starting to make people think maybe we need to, like, rethink our understanding of dark energy a little bit.
So how sure are we about this? Like, are we ready to rewrite the textbooks?
Not quite yet. I mean, it's definitely exciting, and there's a lot of buzz about it, but, scientists are a cautious bunch. Right now, the data supports the idea of evolving dark energy at a level of somewhere between 2.8 and 4.2 sigma. That's a measure of statistical significance. To really, like, claim a discovery, you usually want to be at 5 sigma. That's, like, super duper sure. So we're not there yet, but it's a really strong hint, like definitely something to keep investigating.
I see. So more like a promising lead rather than a done deal.
Yeah.
But exciting nonetheless. Have the folks working on DSI, have they said anything about all this?
Oh, yeah, they're definitely paying attention. Michael Levi, the DSI director, he said that they're seeing some potentially interesting differences, is how he put it, that could indicate that dark energy is, in fact, evolving over time. He's careful to say that these differences might go away as they get more data, but, you can tell he's excited to see what that data shows.
And the other folks in charge, like the co-spokespeople, what are they saying?
Oh, they're on board, too. Alexi Lillifeld-Harnett, she's one of them, and she's, like, super pumped about the possibility of a big breakthrough in our understanding of dark energy. And Will Percival, he's the other one, and he's saying that, yeah, this could mean we need to, like, update our standard cosmological model, and that, evolving dark energy would fit right in.
So everyone's pretty stoked about these hints then. Okay, can you walk us through, again, like how DSI uses that baryon acoustic oscillations thing, the BAO, to track dark energy across, like, billions of years?
Sure. So like we said, BAO gives us this standard ruler, a fixed-length scale, that's imprinted on the universe from way back. And we know how big that ruler should be because it's determined by, the physics of the early universe, which we understand pretty well. Now, as the universe expands, that ruler stretches along with it. So what DII does is it measures how big that BAO pattern appears in the distribution of galaxies at different redshifts, which, remember, means looking at galaxies at different distances, different points in the past. And by comparing those measurements to, like, what we'd expect if dark energy was constant, they could see if maybe dark energy's influence was stronger or weaker in the past.
Cool. Okay, so that's how they track dark energy. But what about, like, what it actually is? I mean, we keep saying dark energy, but what is it?
Right. So dark energy, we think it's this form of energy that's, like, everywhere in space. And it's what's making the universe expand at an accelerating rate. And it's not just, like, a little bit of the universe's total energy. It's, like, the main ingredient. We think it makes up about 68% of the total energy density of the universe. Compare that to dark matter, which is about 26%. And normal matter, the stuff we're made of, the stars, the planets, that's only about 5%.
So dark energy, it's like the big cheese.
Yeah.
But it's also really, really spread out, right?
Yeah. Even though it's, like, the most dominant thing energy-wise, it's got this incredibly low density. Like, way less dense than the matter inside galaxies or even the stuff between galaxies. But because it's literally everywhere, it all adds up. And that's why it has such a big impact on the expansion of the universe.
Makes sense. It's funny, we were talking about Einstein earlier, and it turns out he kind of had an idea about something like dark energy
Yeah.
way back when, right?
Yeah, he did. He called it the cosmological constant. He was trying to make his equations for general relativity work out for a static universe, a universe that wasn't expanding or contracting. So he added this term, this cosmological constant, to balance out the gravity that would otherwise pull everything together. Of course, then Hubble came along and showed that the universe was actually expanding, and Einstein was like, oops, my bad. He famously called the cosmological constant his biggest blunder.
It's ironic, right? Because now we're like, maybe he was onto something after all.
It's funny how things work out, right? Even if he was wrong about why he needed it, that idea that empty space could have its own energy, that was a pretty big deal. It kind of paved the way for our current thinking about dark energy.
So if we haven't actually, seen dark energy, how do we even know it's there? Like, what's the evidence?
It's mostly indirect evidence, but it's pretty convincing because it comes from a bunch of different sources. The biggest piece of evidence came in the late 1990s when scientists were studying Type Ia supernovae. These are a specific kind of exploding star that we can use as standard candles to measure distances in the universe. And what they found was that these supernovae were fainter than they should have been if the universe was expanding at a constant rate. The only way to explain that was if the expansion was actually speeding up, which led them to dark energy.
Right. So it's like these exploding stars are telling us that something's pushing the universe apart.
Yep, that's the idea. But it's not just supernovae. There's other evidence too, like the large-scale structure of the universe, the way galaxies are clustered together in these huge filaments and walls. That also points to dark energy. And there's evidence from the cosmic microwave background radiation too, the afterglow of the Big Bang. All these different things, they all fit together and they all lead to the same conclusion. There's something out there, something we can't see, that's driving the universe's expansion.
Okay, so lots of evidence for dark energy, but we still don't know exactly what it is. Earlier, you mentioned the cosmological constant, and you said there are other ideas out there, too.
Yeah, there are. The cosmological constant, it's the simplest explanation, but it's not the only one. One idea that's been getting a lot of attention is something called quintessence. It's basically this field that permeates all of space, and its energy density can change over time, unlike the cosmological constant, which is, constant. And the DAI results, those hints that dark energy might be weakening over time, they fit better with these kinds of dynamic dark energy models.
So instead of just being a property of space itself, dark energy could be tied to this field that's evolving and changing.
Exactly. And one of the big things scientists are trying to do is figure out the equation of state for dark energy. It basically describes the relationship between its pressure and its energy density. For the cosmological constant, that equation of state is a constant value, exactly -1. But if dark energy is something like quintessence, that value could change over time. Figure out this equation of state. It's like trying to figure out the personality of dark energy, what makes it tick.
That's a great way to put it. And understanding all that has huge implications for the fate of the universe, right? How it all ends.
Oh, absolutely. The way dark energy behaves, whether it stays constant, weakens, gets stronger, all that, it's going to determine what happens to the universe in the long run. If it keeps accelerating, we might end up in this cold, dark, empty universe where everything is so far apart that nothing can interact anymore. Some people call it the heat death of the universe.
That doesn't sound so good.
No, not really. And there are other possibilities too, like maybe the expansion gets so strong that it rips apart everything, even atoms. That's called the Big Rip. Or maybe dark energy weakens and gravity takes over again, pulling everything back together in a big crunch.
So the ending can be pretty dramatic, but okay, zooming out a bit for people listening who aren't cosmologists, why should they care about all this DSI stuff?
Well, I think the big takeaway is that these DSI results, especially when you put them together with all the other evidence we have, they're telling us that maybe our current understanding of the universe is incomplete. We've been thinking of dark energy as this constant force, but what if it's not? What if it's changing? That would be a huge shift in our understanding of how the universe works. It's like a whole new layer of cosmic mystery.
Yeah, it's like the universe is telling us, hey, you thought you knew how this worked? Think again.
Exactly. And even if it all sounds a bit overwhelming, I think the main thing to remember is that we're potentially on the verge of a major discovery, something that could completely change how we view the universe. And DSI is right at the forefront of that.
It's exciting, right? Like, we're figuring out the biggest mysteries of the universe. And it's not just like an intellectual exercise either. Understanding dark energy, it's crucial for knowing what's going to happen to the universe in the future, right?
Totally. Whether the universe keeps expanding forever, whether it slows down, whether it collapses back in on itself, all that depends on dark energy. These DSI results, they're a big step forward in figuring out that story.
And the story's not over yet, right? DSI is still collecting data, and there are other projects and telescopes coming online, so we're going to learn a lot more in the next few years.
Oh, yeah, absolutely. DI's got 2 more years to go, and we're already seeing these tantalizing hints. And there's a whole bunch of new telescopes and surveys coming online soon, which will give us even more data and, different ways of looking at dark energy. It's really a golden age for cosmology.
So to sum it all up, the Dark Energy Spectroscopic Instrument, or DSI, it's this awesome project that's mapping the universe in amazing detail. And its data is giving us some really strong hints that dark energy, the force that's driving the universe's expansion, might not be constant after all. It could be changing over time, which would mean we need to, like, revise our whole model of the
Yep,
universe.
that's a pretty good summary. And that brings us to a final thought for our listeners. If dark energy is really changing, what does that mean about the physics of the universe? What are we missing? Are there new forces, new particles that we haven't discovered yet that could explain all this? It's something to ponder.
Lots to think about. If you're as fascinated by this stuff as we are, we've got a link to the official DI website in the show notes. You can check it out and, learn more about the project and the science behind it. And if you want to go even deeper, do some research on dark energy, the cosmological constant, quintessence, and baryon acoustic oscillations. That's a fun one to say.
It is. Anyway, exploring the universe and its mysteries, it's a never-ending journey, and DSI's findings are like a brand new chapter in that story.
Thanks for joining us for this deep dive into the cosmos, everyone. We'll see you next time.